All right, SPH3U, it's time for me to swallow my pride for a second and do a little video to say I could have done that problem a whole lot better in the last video. I finished recording, I put it online, and then I was like, wait a minute, there was a better way I could have shown people how to do this. So, recap of this problem was we had 150 grams of water on one side, which started at 30 degrees Celsius, and it had a specific heat capacity of 4.184 joules per gram degree Celsius because that's the specific heat capacity of water. On the other side, we had 250 grams of water that started at 75 degrees Celsius, and it also has a specific heat capacity of 4.184 because it's water. And the heat, which I even screwed that one up, look at that. The heat would have transferred from the hot one to the cold one because this one's a higher temperature than this one. So this one would lose energy, this one would gain energy, but I said, you know what? Why don't we do it a little bit of a different way, and we go, how much energy did it take to get this thing from 0 degrees to 30 degrees? And then that's Q equals mCt. We start at 0 degrees, so the delta T is from 0 to 30, so that's 30 degrees Celsius, and that's how many joules it would take after you do the calculation. This one, do the same thing. How much energy from 0 degrees to 75 degrees? Right? Same thing, Q equals mCt, mass, heat capacity, the temperature, get an answer, 75. Then you add them together, you get that much, and then you go, okay, well, then the total mass is 400 grams because I did 150 plus 250, that's 400. And then rearrange Q equals mCt to get T is Q over mc. Do that, right? There's our total energy. It's total amount of energy from 0. That's our total mass, and that's our heat capacity for the two of them together, because it's still just water, so it's the same heat capacity. And then that makes 58.125 degrees Celsius. So, yeah, and because we assumed it was from 0, because both of them started at 0 degrees Celsius in our hypothetical physics world, the plus 58 degrees Celsius from 0 degrees means our final temperature is 58 degrees Celsius. And I was like, yeah, great, it's a good way to do things, it's simple. And then I made a mistake. I said, that doesn't work if they have different heat capacities, so you should use the other, much more complicated method. And then I said that method's faster and more beautiful. Well, I finished the video, I posted it, and then I had to think. And then this morning I got up and I looked at the algebra and I thought, I should make a video about this. So let's look at that second method without numbers, just the algebra, raw algebra on this second method. And the way the second method worked, was we said that Q1 is equal to negative Q2 because the heat from one went into the other, right? That's the assumption we made up here. The heat from one went into the other. So M1 times C1 times delta T1 is equal to negative M2 times C2 times delta T2. Right? Now we're interested in TF. TF is our question mark. So we want to open up that delta T, open it up into M1 times C1 times, and then delta T is the final temperature minus the initial temperature. So T1 is going to be the initial temperature. Minus M2 times C2 times, same thing, the final temperature minus the second one's initial temperature. T2 is going to be the initial temperature of the second one. Then we have to pull out TF. If we want to pull out TF, we're going to have to distribute these in. So distribute them in, meaning we take this guy, M1 times C1, and we're going to put that guy in there and in there. All right, we're going to do the same thing with minus, including the minus in here and in here. And so let's do that. M1 C1 TF is equal to, not equal to, whoops, M1 C1 TF minus M1 times C1 times T1, that's equal to, now the minus stays with it, so minus MCT minus M2 times C2 times TF, right, times TF. And then this minus times the minus is going to give you a plus. So this minus times this minus is going to give you a plus for the next part of it. So plus M2 C2 T2. So that's that. Now I want to collect the terms that are together. Like TF and TF are over here, right? There's a TF here, and there's a TF here. I want to bring together my TFs, and over here we'll just get those over on the other side. So how do I do that? Well, I want to get this away. I want to put that over on this side. It's a minus right now, so I'm going to go plus M1 C1 T1 plus that entire term, that entire number. And I have to do that on this side too, so plus M1 C1 T1. This one here, I want to bring this guy over here so that the TFs can come together. The TFs want to come together. So I'm going to go on this side, minus M2 C2 TF, because I want to bring this entire thing over to the other side. So on this side, that's what I do to this side, I have to do on this side to keep the equation. So minus M2 times C2 times TF. Okay. So minus M1 C1 T1 plus M1 C1 T1 is 0, because it's minus a number and then plus the same number. Minus M2 C2 TF, that would be a plus, whoops. Hey, look at that. Self-check caught it. Self-check caught the problem. Plus, so got a plus. Plus, that's going to be 0. So minus that plus that is going to be 0. But that has to stay there because it can't cancel anything, and that has to stay there because it can't cancel anything. So let's rewrite it knowing what we know now. This is, on this side now, M1 times C1 times TF plus M2 times C2 times TF. Right? And that's equal to, that's all gone, but this stays. And it doesn't matter which order we put them in because it's an addition. Right? 3 plus 4 is the same thing as 4 plus 3. 1 plus 10 is the same thing as 10 plus 1. So I'm going to put the M1 C1 T1 first, and the M2 C2 T2 after it. Again, it doesn't matter which way we do it. Okay, next up, we are interested in TF, right? We want TF. We want TF. So we've got a TF over here. We've got a TF over here. We're going to pull that out because it's multiplying both of these. So we get to factor this expression, and we get TF times, right? TF times these ones together. M1 C1 plus M2 C2. And we'll leave this on the other side, M1 C1 T1 plus M2 C2 T2. Okay. Now we want just TF by itself, right? We just want TF by itself on this side of the equation, and it's multiplied by this entire gigantic thing. So what we do then is we divide by this entire gigantic thing, M1 C1 plus M2 C2. And we do that on both sides because what we do on one side we have to do on the other side. M2 C2. And now we get our final expression. To solve for the final temperature, it is going to be M1 C1 T1 plus M2 C2 T2 over M1 C1 plus M2 C2. Right? There's a big old formula for you. Big old formula for you. But oh, we're not done yet. This is where the magic is about to happen. And where my apology has to come in. Remember back here? Remember what we did? We figured out how much energy it would take to take it from 0. So we did m times c times its temperature. And then we figured out how much energy it would take this one from 0. We did m times c times its temperature. So, 150 times 4.14 times 30, 250 times 4.14 times 75. Well, guess what's over here? Over here we have m1 times c1 times t1. Excuse me. And over here we have m2 times c2 times t2. All right. So they're right there. So this guy up on top, that's the heat from 0 to T1. Right, that's the heat of M1. This guy here, that guy, excuse me, is the heat from 0 degrees Celsius to T2 of M2. All right, same as we did before. And then these guys down here, that guy is the only thing that kind of changes. It's the add the masses. You add the masses, but it's like a weighted average. Right, it's like if you got like 30% of your grade is the exam and 70% of your grade is your other classwork, and you're trying to figure out how good to get on the exam to keep your 80. It's the same kind of thing you're doing. It's the capacity times the amount and plus the capacity times the amount. If it's the same C, which it was in this problem, it's the same C both times. M1 times C1, right? If it's the same C, same C, M1C plus M2C just becomes M1 plus M2 times C. All right, that only happens if it's the same heat capacity for both objects. Right? Oh, that's the two weights added together, the two masses added together, times the heat capacity of the substance, which, oh my god, guess what? That's the two masses added together, and that's the heat capacity of the substance. So, yeah, the algebra checks out. We didn't put any numbers into this. So this is true for any mixing problem. Any two materials with any two masses, any two heat capacities, any two initial temperatures, that will be an answer. So it's the heat from 0 to T1, the heat from 0 to T2. Add them together and divide them by the weighted average of the masses and the heat capacities. Yeah. So conceptually, that's how you can think of it. And it'll give you the right answer every time. It'll even give you the right answer if you're below 0. If you start below 0, what'll happen is this will just end up negative, or this one will just end up negative, but it'll still be fine. You can even flip the two. Because addition is commutative. So 3 plus 4 is 4 plus 3. Down here, addition, it's commutative. 3 plus 4 is 4 plus 3. It doesn't matter which one you put on which side. So yeah, some really wonderful math, and a little bit of me eating my own words from yesterday. So yeah, there you go. Moral of the story, don't make declarative physics statements when you're recording a video at night on a Wednesday after a whole lot of video recording. Yeah, that's it. Thanks for listening to my spiel, and I'll see you guys in class.